Today we are going to do section 6.5 on page 737. But before that, I want to go over some old concepts that we have already learned, but it might have forgotten or don't remember that clearly. So let's go over. Well, most of these we learned fairly recently, but they are somewhat confusing because they're similar and then you might not remember them exactly. So first, let's look at Theorem 6.12, Green's theorem circulation form. What that means is that when you integrate over a closed curve, and then if this is on 2D, right? F equals to just PQ, no third dimension. So on 2D, when you integrate over a closed curve, then it equals to the theorem states that when you integrate along the curve of p dx plus q dy, that's the same as integrating over the area, d, where the curve is surrounding, and calculate qx minus py dA, and that's the circulation form. So we have done some homework on that, and so we will, next, the flux form. Now the flux form looks similar to a circulation form, but the flux form has a different definition. Okay, it's f dot nds. Now in that case, then again f is f is in 2D. F is only pq. And then if that is the case, then the integral then becomes px plus qy. Notice there's a slight difference of the formula, right? Because that's the flux form, you're integrating something different. The top one, you're doing f dr, and the bottom one, you're doing f dot nds. But other than that is the same principle. Well, similar principle. When you're doing qx minus py for the circulation form, the other one you're doing px plus qy, and that's for the flux form. All right, so next we go to some other page a bit later where we talk about what is a source-free field. Now that's a quite recent concept, but we're going to go over it anyway because there are several conditions and it might be hard to remember. Now the source-free field, the flux of see the flux form, the flux across any closed curve is 0, okay, which means the flux is independent of path if f is for a source-free field, okay, if f is a source-free field, then the integral along two different paths is the same. That is, it is independent of path. The third condition is that if f is a source-free field, that means that you remember all these things are equivalent. That is, they're all the same. They mean the same thing. Okay, a source-free field also means that there's a stream function g such that where f is pq, right? We're talking about 2D right now. If f is pq, then there exists some kind of stream function such that p is gy. That's the partial derivative, and q is minus gx. And then it also has that dot property that we won't pay attention too much right now. And number 4 is px plus qy equal to 0, and for a source-free field. So that's good. And finally, I want to remind you of something we did, maybe 100 pages ago or something. What are we doing? Nope, I missed that page. Try again. The cross-partial property. That is, if there is such a thing as a cross-partial, on certain conditions, I know, conservative vector fields. If f is conservative, all right, and we're talking about a 2D situation and a 3D situation, either way. But in the 2D situation, then py equals to qx. In the 3D situation, you have that bunch of equalities down there. But the point is, and you're going to need this theorem today, is there are various things that are equal is the cross-partial property of conservative fields. All right, so with that, we are ready to look at the divergence and curl chapter. So let's go to page 737. And first, let's look at the definition. what is a divergence? What is divergence? Okay, now divergence is defined very simply, as you can see on the page, that by the partial derivatives. That is, if you have an f equals to PQR, then or in 2D just PQ, either way, the divergence is the sum of the partial derivatives added together in such a way. That is specifically not all the partial derivatives, just P each one, okay? Like the one in the x component, you will take the partial with respect to x, and Q with y, and R with z, etc., and you add it up. And that thing that you just created is called the divergence. Now the divergence is, in 2D, of course, you only got Px, see down here? 2D have only Px and Qy to talk about, but the principle is the same. One way to remember the divergence is it is also called del dot f. That's because del represents the partial operator. Okay, you're not actually doing any dot product. That's just a mnemonic device to help you remember what the divergence is. So that's why the divergence sometimes also written with a del operator, del dot, to help you remember how it works. That is, you apply the operator on each item, and then you add it all up, just like doing a dot product. So that's divergence. And excuse me. Now, having said that, let's look at an example. Go over a couple of pages there. We are calculating the divergence of a point, example 6.48. Please do that as part of your homework. As you can see, it's very straightforward. You just take the partial derivatives, add it up, and you're done. And okay, so next, let's look at the next example, example 6.49 on the following page, where it says right on top of the example. Now, anytime the example says something weird, just look right on top of it because it will explain it. In this case, it says, is this thing magnetic? And you're like, what's that supposed to mean? Well, look right on top of the page where it says the divergence of a magnetic field is 0. So in other words, the book wants you to figure out if the divergence of this thing is 0. So you go ahead and calculate it. And after one line, then you realize it's not. Because the divergence is not 0. So, so please do this as part of your homework, example 6.49. And then look to the bottom of the page. We are now on page, we're still on page 740, where we are looking at the first theorem, which states that, what is it? If f equal to pq, so this is just a 2D situation, okay? So f equal to pq is a source-free vector field with differentiable components and stuff, and it's continuous, etc. So all kinds of nice conditions, no weird folds or corners or something or hole in it. So if it's a source-free continuous vector field with differentiable functions, then the divergence of f is 0. Now remember what we said a few moments ago, what is source-free? It means those 4 or 5 things that I said, okay? And but therefore to prove it, however, is actually very straightforward once you realize, based on what you see about the source-free business. So please do the proof, which is 1 line long, of theorem 6.14 as part of your homework. And the next theorem is not so easy, so we're not going to prove it, okay? You're just going to believe it, which is 6.15 on the following page, 741. So next, let's go to page 741, where we have a theorem too hard to prove, but it states that if f is a continuous vector field, differentiable components, domain is simply kinetic, so all kinds of, well, let's just say easy requirements. Then the divergence of f of 0 means that f will be source-free. The other way is also true. If f is source-free, then the divergence of f is 0. We already said that, but we haven't said the first one. But we're going to state that now. That is that divergence of f equal to 0 implies that f is source-free. Now, with that, please do example 6.50 as part of your homework. and then we'll go to the next point. There are certain, I guess, interesting notice that you might see. For example, at the bottom of this page, 741, you notice that your book mentions that being that the flux form of the Green's theorem says that, okay, here's the flux form. Is it? I will check in a second. So the flux form Green's theorem says this, which we looked at a moment ago, okay? And it just happens that divergence F is Px plus Qy. So you can also write it this way, okay? That is, the flux form of Green's theorem can be written, you can stuff divergence in there for Px plus Qy. Yep, you see, it is the flux form, okay? The flux form is F dot nds, which is Px plus Qy. We saw that a moment ago. Next, let's look at examples 6.51 on page 742, where we're talking about, your book is asking, is more flowing in than flowing out? You're like, what's that supposed to mean? Then look at the paragraph right before it, where it says the divergence bigger than 0 means that more fluid is flowing out. Less than 0, more fluid is flowing in. So you go ahead and calculate divergence, and then figure out whether it's flowing out or flowing in or not. And as you can see, the answer comes out after one line. Okay, so that's that. And then let's go to the next part where we figure out what the curl is. What's curl? Let's look at the next page, 743, where the definition of curl is given. And the curl definition is more complicated, all right? Well, it's not that complicated, but the curl, unlike the divergence, which is just a quick sum adding up of several partial derivatives, the curl is the cross product operation. In other words, you see this stuff being subtracted and all, that is the cross product. I mean the curl. The curl of F is it consists of 6 items that you have to calculate Px, Qy, and Rc the same as before, but then you have to do this, okay? And notice the curl of F is defined as some kind of a vector field. That is, it has 3 components in all 3 directions. Now to remember the curl is that you use this mnemonic device. The curl is the divergence is defined as the del dot F, right? To help remember how to do it. Not that you need that much help, it's fairly straightforward. But the curl is not so straightforward. It has all that stuff being multiplied and subtracted and whatnot. Actually not multiplied, just subtracted. So to remember the curl, we will use the determinant location because it happens to work out. That is, this thing is the same as this thing if you were to apply it. And you're not actually calculating any determinant because the operation there isn't a number, but it helps you remember how to do this. See, it just, you remember which partial applies what and which one's subtracting and dividing, and it all works out. So that's how we sometimes remember how to do the curl. Or if you can't remember that, let's just look up this definition, okay? So that's the curl of function f. And then let's look at the next page, okay? It's page 744, where that was what I just showed you is the curl in 3D. Now, what if it has only 2D? In 2D, the curl of f is exactly this thing right here, okay? You just have px plus qy, and then times k. That is, in 2D, the curl of f just points straight up in the z direction, the k direction, and it's just qx minus py. And and so in the 2D, you don't have to worry about the cross product or any of that stuff. It's somewhat simpler. Well, anyway, so let's find the curl of something. You just, do this, right? Do this cross product thing, del cross f, and then the answer pops out nicely and easily if you don't mess up, which I did many times when I was doing the homework of this thing. I'm not good at doing determinants, okay? I'm always forgetting to subtract, add, and multiply. I'm always messing up. But anyway, please do example 6.52 and don't mess up like I did. And the same as example 6.53, it's find the curl of something. Yeah. and keep going. Now, by now, you might be wondering, what does divergence and curl mean? As math students, we don't care what it means, okay? We just know what it is, and we move on. Anyway, and your book tries to explain what it means, but it's not really giving a very good explanation, because to know it, you need to study advanced physics. This isn't even taught in the regular Physics 101 class. So I can't just tell you, well, why don't you go study physics? It's not that simple. This is just, but we're math students. We don't care what it means. We just do math, right? So let's look at this and look at the next page. Now I'm on page 745, where we look at something, 745. And I want to mention something real quick. That is, this particular situation that we just memorized is that the curl is on a 2D is simply qx minus py dot k, times k, okay? Which, or put it in other ways, if you take it and the dot k, then it's just equal to qx minus py. And what is qx minus py? It happens to be the circulation form of the Green's theorem, which we looked at a moment ago. Okay, here's the circulation form, right? The minus one is the circulation form, whereas the plus one is the flux form. So it just happens to be the same. And as a result, this particular equation stands on for f in 2 dimensions, right here. This f dr, you can also write it as curl f dot k dA. And because the dot product just happened to give you the same thing, which is qx minus py. So at the bottom of the page, there's example 6.54. And then it says something about no spin. What does that mean? Well, you look at the paragraph before it, basically it says the curl equal to 0 is what you're trying to prove. Yeah. And then so go ahead and show that this particular thing, the curl has no 0, example 6.54, which is a few more lines, but is not that much more, okay? A few lines, then you're done. So please do that, example 6.54, as part of your homework. And then next, we are going to, you're going to wonder, what are we going to do with all this stuff? Nothing. We are just going to see how to do this math and not worry about what we're going to do with it. So let's look at example 6.16, which says that if you have a vector function in a vector field in R3, I don't know if I mentioned that before, but you see this funny way of them typing the letter R right here? Let's see, is it focusing? Yeah, right here. Okay, I don't think I mentioned this before, but when they write it like that, that means all of space. That is, R3 is the entire 3-dimensional space, whereas R2, with the same funny-looking R, is the plane, okay, the 2D plane. That's all that means. Anyway, so let's look at theorem 6.16, which states that with proper conditions, all component functions have continuous second-order partial derivatives. Okay, so what's second order? That's the second derivative, okay? That is fxx, fxy, that kind of thing. So if that is true, okay, then the divergence of the curl, which is defined as del dot del cross f, it happens to be 0. Now, if to prove that is just a matter of 2 lines, okay? So please prove that by yourself. Just remember Clairaut's theorem, which states that when things are good, like nothing, no folds, no nothing, everything's continuous, differentiable, blah blah blah, then a function, when you take the mixed partials, that is fxy, is the same as fyx. So once you do that, then everything comes out pretty nicely. So next, please do example. So please prove that yourself. Okay, that's part of your homework, being that it's just 1 line long, or 2, or whatever. And so please prove theorem 6.16 as part of your homework. And let's move on to example 6.55. And you're doing some curl thing, as you can see, the answer is in 2 lines. So please do that as part of your homework. Now next let's look at theorem 6.17 on page 747. That is, which says that, I missed the page, there. Okay, if you have a vector field F with that in 3 dimensions, PQR is conservative, then the curl F happens to be 0. Okay, and that is again a very short proof that's based on that cross partials property that I mentioned a little earlier. So please do that proof, a one line or so proof as part of your homework. And then, so that's theorem 4.7. Let's keep moving. Theorem 4.6. That is, says it the different opposite way, but that is, if F is a vector space on a simply connected domain, if curl F is 0, then F is conservative. Again, the proof is about a line long and has something to do with the cross-partial properties that we mentioned a little earlier, so please do that as part of your homework. And with that, please do example 6.56, where you test whether a vector field is conservative. And the answer, as you can see, is about 1 line long. Okay, very nice and comfortable. And finally, we're talking about, your book is talking about harmonic functions. Is this thing electrostatic field free of charge? You're wondering, what does that mean? It just means that it is, well, look at the description before it. It has something to do is harmonic or something. Harmonic means here's harmonic. What harmonic means is fx. Look at the part right before the example, right? Harmonic means we have seen it before, which means the fxx plus fyy plus fcc, which is also written as del squared. Okay, a equals to 0 is what that means. So if you check to see if the second derivative add up to be 0, then it's harmonic, and therefore something to do with electrostatic, which we really don't care. Okay, we only care about if it fits into the harmonic situation. So with that, we have come to the end of the section. Now for homework, please do on page 750, please do problems 219, 29, 237, 47, 55, and 65. There's not much homework in this section because there's really not much to do. You just calculate the divergence of something and then the curl of something, and that's about it. So, so please do that, and that's the end of this section.